Let's look at number 14 in section 2.3. We're finding the limit as x approaches 4 of the function f of x, where f of x is this piecewise defined function. A piecewise defined function simply means the rule for the function that determines the output to the function is based upon the input's value, where it's a defined on the domain is different, right? So in other words, if the input x, the domain value is less than 4, we use this expression. If the value of x is equal to 4, we use this. In other words, if we plug in x, the output's going to be 6. If I plug in an input greater than 4, we use this rule. That's what this piecewise defined function. We can actually graph this. I'm not going to do that, and that can give us some graphical insight as to whether or not this limit exists. First of all, just note, again, as we say, since the function is equal to 6, if x equals 4, I know f of 4 is equal to 6. This tells us nothing about the limit, right? The value of the function being equal to 6 does not mean the limit is equal to 6, right? Again, I can have a function and the value of the function at 4 can be 6. Put a little dot there, right? But the function can still have the limit exist and right? The limit is something less than 6 in this case, or the limit may not even exist. And so we don't know. The value of the function doesn't tell us what the limit is necessarily. Okay, so how do we do this? Well, we're going to take a look at the limit from the left and from the right. The limit from the left of 4, or the limit below 4. So what is the limit as x approaches 4 from the negative side for this function? Well, if I'm approaching from the negative side, meaning we're less than 4, I have to be using this formula, right? So in other words, I'm looking at the limit as x approaches 4 from the negative side of 2x plus 5. Well, this function is continuous, right? And so this limit exists, and because it is continuous, we can simply plug in directly, okay? We actually talk about continuity, I guess, in the next section, so I should emphasize that we're really using the basic limit law. So let's keep it that way instead of talking about continuity. In other words, this would be equal to right, 2 times the limit as x approaches 4 from the negative side of x plus the limit as x approaches 4 from the negative side of 5, right? This limit is 4 because I can, right, because this is just approaching x, and this limit is 5 since 5 is a constant, and I get 2 times 4 plus 5 as I've written here, which is 13. So I'm really using the basic limit laws. Okay, kind of got ahead of myself in this section. We haven't yet talked about continuous functions, so we'll be getting there in the next section. Okay, the limit from the positive side, right, as we approach 4 from above, now x is greater than 4, so our output's determined by this formula. So we're looking at the limit as x approaches 4 from the positive side of this function. Again, I'll use the basic limit laws like I did here, and you can see when I do that, I'm going to get this expression here, which is also 13. Since the limit from the left and the limit from the right are both equal to the same value, our two-sided limit, if you will, the limit as x approaches 4 of that function has to be the same thing. Okay, so in this case, the limit does exist. Now, suppose in one of these cases, say I get the limit as x approaches 4 from the negative side is 13, but here I get the limit, let's just pretend, let's say this is equal to 15 here instead of 13. Since both limits exist, but are not equal, the two-sided limit as x approaches 4 does not exist, right? Both of the, in order for the limit as x approaches 4 to exist, both one-sided limits have to exist and they have to be equal. Okay, so that's important. If these two values both exist but they're not equal, then this limit does not exist. And I think in the directions you would write DNE for that. Okay, I hope that this makes sense on this one.